Bismillahirrahmanirrahim. Assalamu alaikum. Okay, if you any question in the previous week lecture, you may ask for questions before we start our today's lecture. Just tell me your name and ask for a question. If there is any, please. Any question? Okay, if there are no questions, so first of all, let me give you of design of a bending moment. Design for one bending moment along the east-west direction. We completed the analysis of flat slab along the east-west and north-south directions, both for column strips and metal strips in the last week lecture using the direct design method. Okay, now let me just quickly demonstrate how these flat slabs are then designed after the analysis is completed. I will start with one example. Bending moment of the column strip, interior bending moments for a column strip of the interior frame is selected, and you know that this value is 28.3. So for this 28.3 foot kip bending moment, let's design the column strip, and we will calculate the reinforcement required to be used as stop bars in the column strip for this bending moment. Okay, and once the area of steel is calculated for this bending moment, or all other bending moments, the unit rule can be used to calculate reinforcement. So the bending moment is 28.3 foot kip. Okay, this is MU basically for the column strip negative bending moment. To convert this into inch kip, multiply this by 12. So this comes out to be 339.6. Let's say it is 340. 340 inch kip is the bending moment for which we will design this flat slab. We will assume small a in the beginning is 1 inch. Calculate a is mu 340 divided by 0.9 divide minus 1 divided by 2. When you do these calculations, you will see that the area of steel comes out to be much divided by 0.9. By 8. Okay, so we were discussing the calculation of area of steel for 28.3 foot cube. Okay. When you complete this trial and success method, finally you will calculate area of steel equal to 0.8 square inch for this bending moment. So now for the rest of the bending moments, you can calculate AS using the unit rule like this. For 28.3 foot kip, bending moment area of steel came out to be 0.8 square inch. For any other bending moments, let's say 16 foot kip, steel. 0.8 into 16 divided by 28.3. 0.8 into 16 divided by 28.3. 0.42. Okay, in this manner, you can calculate area of steel for all the bending moments using this unit rule for the north-south as well as the east-west direction for the negative and positive bending moments. Okay, once you calculate area of steel for the bending moments, then you need to calculate the spacing for the bar to be placed inside the slab. So let's say we now decide to use number 5 bar. Number 5 bar has an area of steel equal to 0.3 square inch. Okay, for area of steel equal to 0.8 square inch, which was area of steel required in the column strip interior negative bending moment location. We can calculate spacing by area of bar, which is 0.3 square inch divided by area of steel required into 12. This comes out to be 4.5 inch center to center. Similarly, we can calculate spacing for all other area of steel in the required locations. But finally, while for every bending moment, there will be different spacing, and there will be too many different spacings required inside the slab. Practically, it will be almost impossible to keep so many different spacings inside one slab. So finally, we will round up or round down some of the spacing, and we'll try to keep the spacings not too many. The variations in the spacing shall be not too many, because then it will create problem for the fabricator. So what we do is that we will then look at our analysis results, and we will try to group them in such a manner that fewer spacings are required inside the slab. For example, in this negative interior column strip negative bending moment is 28.3, but then exterior column strip bending moment is 26.8. So 26.8 and 28.3, they are very close to each other. We can say that, for example, if we recommend a spacing of number 5 at the rate of 4 inch or 4.5 inch center to center for this spacing, the same spacing we will recommend for the exterior column strip negative bending moment. Okay, and if you look at the exterior negative bending moment in the interior column strip as well as the exterior column strip, they are almost same, 14 and 13.26, and 14 is almost half of 28.3. So the spacing for this will be double. So we can say that number 4 at the rate of 8 inch or 9 inch center to center will be enough for this. So in this manner, both the bending moments along the north-south and east-west direction, for both the bending moments along the north-south and east-west direction, area of steel can be calculated, and then final spacing recommendations can be done by grouping the area of steel so that spacing variation is kept as minimum as possible. So finally, if you look at this east-west direction design, we have area of steel number 5 at the rate of 4 inch in this location, as well as here number 5 at the rate of 4 inch and here. Okay, at the exterior negative bending moment is number 5 at the rate of 8 inch because it is B. Okay, in the exterior negative, number 5 at the rate of 8, number 5 at the rate of 4. For positive bending moments, here, if you remember, the bending moment was around 16. So number 5 at the rate of 8 in center to center is enough for this. In the middle strip, C means that number 5 at the rate of 12 inch, because the bending moment was less than the bending moment, positive bending moments in the middle strip was less than the bending moments of the column strip positive bending moments. So we cannot keep them same for the sake of economy. We must have to increase the spacing in the middle strip positive bending moment. So we'll keep this number 5 at the rate of cooling center center. Every designer will come up with different spacing and different arrangement of bars in the final design, depending on the area of steel he chooses for his final design and the spacing arrangement. So anyhow, too many different spacings is not good for the sake of fabricator facilitation, and also it will become the drawing will become also very difficult to be carried out at the site. So with this, we complete our design of flat slab along both the directions. So the flexure design, once the flexure design is completed, there are some recommendations of the ACI code, general recommendations, which also shall be fulfilled. These recommendations on the this slide are with regard to the maximum spacing and minimum reinforcement as per the ACI code requirement. When spacing is finalized, it shall be kept in mind that the spacing shall not exceed twice the thickness of the slab. In this case, slab is 10-inch thick, so the spacing shall not be more than 20 inches in both the directions, but only for the critical locations. Okay? And minimum reinforcement shall also not be less than 0.0018 BHF. In this particular case, you know that B is 12-inch and HF is 12 multiplied by 10. So you can calculate area of steel minimum for this, and area of steel at all critical locations. Critical locations are mid-span location for positive bending moment and support locations for negative bending moments. At any other location, the area of steel can be less than this and the spacing can be more than that. Which means that for positive bending moments towards the end, if spacing is more than 20 inch, it is okay. And if area of steel is even less than this, it also is okay according to the ACI code requirement. These requirements are only for critical section. So 0.216 square inch, 0.216 square inch is the minimum reinforcement which shall be placed at all critical locations. The reinforcement shall not be less than this, and the spacing shall not be more than 20 inches. Next is the cover requirement. You know that 3 by 4 inch cover is required both for positive as well as for negative reinforcement for the fire protection and corrosion protection requirement. Reinforcement placement. If you remember, in the case of two-way slabs supported on beams, sharp direction bars were placed closer to the top or bottom surface of the slab because of the fact their short direction bending moments were found to be more than the long direction bending moments. Okay, you know this. However, in the case of flat slabs and flat plates, when there are no beams, then the long direction bending moments are more than the bending moments along the short direction, and for this purpose, top and bottom reinforcement along the long direction is placed closer to the top and bottom of the slab respectively in order to give us larger effective depth. Which means that in this particular case, the reinforcement along the 25 feet direction shall be kept closer to the bottom in the case of positive reinforcement and closer to the top side of the slab in the case of negative reinforcement. The short direction reinforcement shall be kept on top of that in the case of positive bending moment and below the bar in the case of negative reinforcement. Splicing. Splicing will be frequently required, which you know that lapping is the general method of splicing. Lapping by splicing is allowed in the slabs, but it shall be avoided in the critical location. Positive reinforcement, the lapping shall be avoided in the midspan of the slab, and the lapping shall be carried towards the end of the slab. Most probably, the lapping will not be required because for negative reinforcement, the bars in the slabs are curtailed 100%, 8L/3 on both sides of the support. So the lapping will not be required in negative reinforcement. But in the case of positive reinforcement, know that the reinforcement will be placed from one end of the slab to other end of the slab. The lap length shall be provided for the requirement of ACI code you have seen in the know the requirement of the lapping is per ACI code. So the lapping shall be provided, lap length shall be provided as per the ACI code requirements. And then there is a requirement of continuity of bar for structural integrity. Within the column strip, out of all the reinforcing bars, 2 bars will be placed such that they pass through the column core. The column core is basically the portion of the column which is enclosed by the stair. This is total column, and so within the column, this part is basically which is the stair part. This will be column core. So 2 bars will be placed such that within the column strip total, out of the total column strip reinforcement, 2 bars will be placed such that they pass through the column core in this manner. Okay, as shown in this slide. And the remaining bars will be placed according to the spacing requirement which has been obtained from the design. Okay, the placement of negative and positive reinforcement. As I said earlier, that negative reinforcement will be curtailed 100% on both sides of the column support in this particular case, L/3, L/3. So probably lapping will not be required in the case of negative reinforcement. Okay, in the case of positive reinforcement, since bar will be placed from one end to another end, so lapping will be required. This is the general requirement for curtailment of bars, negative bars. Positive bars are usually not curtailed in the case of slab reinforcement. Negative bars are curtailed 100%. If you remember, in the case of beams, negative bars are not curtailed 100%. Some of the bars are carried towards the ends, at least 2 bars, because they are necessary for holding the stirrups. And positive bars are sometimes curtailed in the case of beams, and sometimes they are not curtailed depending on the situation. Okay. In the case of slabs, however, mostly the positive bars are not curtailed. There is another requirement of the code which says that in the case of a corner panel of the overall slab system, corner panel, extreme corner, okay, reinforcement both on the top side of the slab and bottom side of the slab shall be provided as per the given requirement of the code. The requirement of the code is that this mesh shall be provided. This mesh shall be provided at the extreme corner of the corner panel, and this reinforcement shall be equal to the maximum positive reinforcement. Maximum positive reinforcement here at the midspan, both the top and bottom bar. For example, the spacing here for this corner panel is, let's say, number 5 at the rate of 18 center to center. So these bars in both directions, this mesh shall be provided at number 5 at the rate of 18 center to center, both on the top and bottom side of the slab. If it is less than number 5 at the rate of 18 center, but if it is more than number 5 at the rate of 18 center to center, if it is already more than this, then there is no need to change that spacing. This and this mesh shall be provided from the center of the column to a length equal to L by 5 of the panel. For example, if the length 5 feet this side, if this is 20 feet, so this will be 4 feet. So 5 by 4 feet, in this 5 by 4 feet portion, this mesh will be provided with a spacing equal to the maximum spacing of the positive reinforcement in the same panel. Okay, this has been written over here. The positive and negative reinforcement should be of size and spacing equivalent to that required for maximum positive reinforcement in that panel. Okay, next are through the two examples which I would recommend that you practice. This example one is an example with the same dimensions, 25 by 20 feet, but the loads are different. The slab in this case supports a live load of 60 pound per square foot instead of 144 in the previous example. And the superimposed dead load is there, 40 pound per square foot, unlike the previous case where it was 0. The columns are still 14-inch square, like the previous example. FC prime and Fy material properties have also been changed this time. So you can practice this and calculate the bending moments along the north-south and east-west direction in the manner which was demonstrated to you in the previous week. The final values we have calculated for you, and you can compare the value that you obtain from your analysis with these results. East-west direction and north-south direction. Similarly, there is another example where the dimensions have been changed, 20 by 15 feet dimensions, and the live loads is 60 pound per square foot, superimposed load is 40 pound per square foot. Columns are now 12-inch square instead of 14 FC prime 3 and 40 KSI. The data, required data is this slab thickness 8-inch, expected load is 0.264 per square foot, and column strip width is 3.75 feet. I would recommend that you start practicing this using the coefficients that we have discussed in the previous lecture. And I will give you 10 to 15 minutes to calculate the values along the east-west direction in the interior frame, and then calculate the bending moments along the long direction, along the east-west direction in the column strip, as well as in the middle strip. So please do this and then compare your values with the values given on the next slides. Okay, we'll share the values with you once you calculate your values. So practice this in 10 to 15 minutes. Find out the values along the east-west direction in the interior frame, in the column strip as well as in the middle strip. And then we will discuss the remaining part of this lecture, which is session 2, on the design of flares for punching shear. Okay. So I will give you now 10 to 15 minutes to do this, and then we will discuss. Okay, before we start our uh, session 2 on the design of flared slabs for punching shear, if you have any question, you can ask your question, please. Any question from anyone? Okay. If there are no questions, let's start our next session 2 of the punching shear. This summary of this method, direct design method. Okay, in the session 2, we will discuss the shear design for two-way slab system without beams. These are the topics to be addressed. You know that flat plates are provided as flat plate is the system without beams. And the most common problem with the flat plate is the punching shear problem. To avoid the punching shear problem, drop panels in the form of a thick part of the slab in the vicinity of the column, or the increased size of the column at the head of the column, which is called as column capital, are provided as shown on the in the right side of right figure. Okay, we have discussed the background of the use of flat plates and flat slabs as an alternative to slabs with beam system. Their advantages and disadvantages have also been discussed. The problem of punching shear is more or less similar to a case when a piece of paper, for example, is supported on paper pins. You know that paper pins can make a hole in the piece of paper. Okay, and the heavier the piece of paper is, the more likely the needle will make a hole in the piece of paper. And similarly, the thicker the piece of paper, the difficult it will be for the needle to make a hole. So the thickness of the paper will decrease the probability of punching the paper. In the same manner, the thickness of the slab will decrease the probability of punching slab. Okay, and for this reason, in the case of flat plates, drop panels are provided in order to avoid the problem of punching shear. And sometimes column capitals are provided, and the column capitals are just like increasing the size of the needle in the case of needle and paper example. Okay, if the needle size at the top of the needle where it supports the piece of paper is increased, then the possibility of making a hole in the piece of paper will be decreased. In the same manner, column capital is provided where when the punching shear problem is intended to be controlled in the case of flat plates. The punching shear is a problem in case of flat plates. This problem can be avoided by either increasing the thickness of the slab. The overall thickness of the slab can be increased, which will further increase the weight of the slab. Or by increasing the size of the column, the size of the column can be increased along the length of the column, which will increase the size of the column from end to end, and thereby unnecessarily the cost of the project will increase. So in order to eliminate this problem of punching shear, the drop panel and column capital are provided. One of them or both of them can be provided at one and the same time. Okay, there are ACI code requirements for the provision of column capital and drop panel, which will be discussed in the next slides. Okay, the problem of punching shear is I tried to explain with the example of piece of paper and needle that it is the weight of the slab which basically causes punching. When the slab is supported on columns, then the weight of the slab acting downward will cause a shear along the faces of the column and will try to slide along the face of the column. It has been experimentally observed that this shearing or sliding of the slab will not occur at the face of the column, rather it will occur at this angle which is being shown here. And this angle is roughly 45 degree with the horizontal. Okay. So when the slab tends to, when the slab acts downward, this sliding will occur along the length of the crack in this manner. Excuse me. Okay, along the crack in this manner. So, which means that this part of the slab on the right of this crack, this part of the slab which has come down, is basically causing this shear. So, for this reason, the critical punching shear is calculated away from this crack, just like the case of the beam shear. In the case of beam shear, if you remember, we used to take critical shear at a distance of d from the face of the support, instead of taking this at the face of the column. At the face of the column or at the center of the column, there will be no doubt maximum shear, but the shear, critical shear, which is to be used in the calculation of shear reinforcement, that is taken at a distance of d from the face of the support. And the reason for this is that when the sliding occurs along this crack in this manner. So the right part of this beam, the right part of the beam will slide against the left part of the beam along this crack, which means that this part of the load, the load on the right part of this beam will basically cause this shearing, because the left portion load will be directly transferred to the column, and this will not contribute to the shearing of the beam along this crack. For this reason, the critical shear is taken at a distance of d from the face of the column. In a similar manner, the critical shear in the case of punching shear is taken at a distance of d by 2, and the green area is used as tributary area for the punching shear. This tributary area is calculated in this manner. For one of the interior column, this can be calculated very easily. And you know that while we were discussing the design of isolated column footing, there we discussed the punching shear problem, and we also discussed the critical shear parameter B naught. This critical shear parameter B naught is calculated from this dotted line parameter at a distance of d by 2 from the face of the column on all sides for this interior column. So B naught basically is equal to 2 into C1S plus D plus 2 into C1L. L is the longer side of column. C1 means the column dimension along the long side, and S means the column dimension along the short side. So 2 means this side. For example, if this is the short side, this is also the short side parallel to this. So this length into this length plus d by 2 plus d by 2 on this side. Similarly for the long side. This is called as the critical shear parameter. This needs to be calculated for the calculation of punching shear capacity as well as punching shear demand, which is demonstrated in the next coming slides. So the critical shear parameter for an H column is calculated in this manner because the column does not extend on this side. So we have two sides on this and one side on this side of the column. So these two sides will be 2 into C1s plus D to D by 2, and this will be 1 C1L plus D by 2, and D by 2 means D. Or in carbon column, similarly, you can calculate B naught this manner. Okay. Next is the demonstration of calculation of punching shear. Punching shear. Punching shear demand. Punching shear demand. B naught is equal to 4 into C plus D. And the tributary area, the green area, can be calculated from the total area minus this area inside this location. So L1 into L2 is the total area, and this area of this C plus D whole square. So this C plus D whole square area is deducted from the total area, and this will give you the tributary area. Okay. The total punching shear load is L1 into L2 into WU. But since this area is not contributing to the punching shear, so this will be deducted from this. Punching shear demand is VU into WU into AT. Okay. Now the punching shear capacity, the total punching shear capacity 5VN will be equal to 5VC plus 5VS. 5VC is the concrete contribution alone, and 5VS is the reinforcement contribution if there is any. 5VC is calculated from these three equations according to the ACI code, and the least of these values, the least value of all these three values shall be selected as 5VC. This first equation is 4 into C prime B naught D. Every term in this equation is known to you. In this equation number 2, beta C is a new term. Beta C means longer side of column to shorter side of column. For a square column, this will be equal to 1. So for a square column, this will become 2 plus 4, 6 times FC prime B naught D. And for a rectangular column, for example, if the ratio to long to short is 2, this will become 4 divided by 2, 2 plus 2, 4. Again, it will become like this equation. The third equation is phi alpha S D B naught plus 2 FC prime B naught D. Alpha S is, this is specifically for a column with the interior column dimension. When the column is interior column, this alpha S will be equal to 40. So this will become 40 into D divided by B naught. Okay. And for an edge column, this will be 30. For a corner column, for interior column, it will be 40. For edge column, 30. And for corner column, it will be 20. Okay. When 5VC is greater than VU, so nothing will be required. 5VC, when 5VC is greater than VU, nothing is required, which means that no reinforcement is needed, no drop panel, no column capital, nothing is needed. The slab thickness alone is enough to take care of the punching shear demand VU. Okay. And if you compare this case with the case of beam shear, in the case of beam shear, if you remember, we said that when 5VC by 2 is greater than VU, then nothing is required. But here in the case of punching shear, when 5VC is greater than VU, then there is no further action required to control the problem of punching shear. Okay. However, when 5VC is less than VU, then either we will increase 5VC by increasing the depth of the slab, because 5VC is a function of depth of the slab. With the increase in depth of the slab, 5VC will increase. 5VC is also is a function of B naught, and B naught is then a function of D and C, column dimension and depth of the slab. So if we don't want to increase the depth of the slab, or if we don't want to provide the drop panel, then column capital can be provided by increasing. B naught can be increased by providing column capital. Similarly, we can also increase FC prime, because FC prime is also a function of 5VC. However, if none of these is possible, then we will provide shear reinforcement. Okay, and shear reinforcement can be provided in the 4 forms. The most common is to provide an integral beam. Integral beam is a short beam which is placed inside the slab on top of the column in this manner. I will zoom in this so that you understand this. 2 bars top and 2 bars bottom, 2 bars top and 2 bars bottom, and then strips are provided, and these are short beams not provided from one column to another column. These are short beams, mostly 4, 5, 6, 8 feet long, and they are contained inside the slab, which means they don't project outward from the slab. And the reinforcement, the shear reinforcement, is also provided in the manner shown in the slide. So this is called an integral beam. This is the most common shear reinforcement provided for punching shear. Okay. Another form is to provide bend bars. Bend bars are provided in the location where there is a possibility of punching shear crack occurrence. So bend bars are provided in order to intercept the crack at that location. Because the crack will occur in this direction, so the crack will be intercepted by these bars. Okay, however, this becomes challenging to provide these bend bars at the correct location in the field. So for this reason, in most of the practical conditions, integral beam is provided instead of bend bars. The third form of shear reinforcement is what is known as shear head reinforcement. Shear head reinforcement, steel I sections or W sections are provided, again 4, 6 feet long, contained inside the slab. One I section is provided is in the full length, and the other is provided half on one side and half on the other side, and then welded to the previously placed section. Okay, this will make a plus sign on the top of the column, and this is called shear head reinforcement. The last form of this punching shear reinforcement is shear stud reinforcement. Shear stud reinforcement is provided in this form. These are steel plates, and the top anchors or steel nails are provided. They are welded with these plates, and they are provided in the plane. They will look like this, and in the section they will look like this. Okay. As I said earlier, the most common form is the integral beam, so we will discuss only the integral beam design in this lecture. Okay, first of all, let's see if drop panel is to be provided. What are the requirements of the ACI code? There are two requirements of the ACI code if a drop panel is to be provided in order to control the problem of punching shear. Number one is that the size of the drop panel shall not be less than the requirement given on this slide by the ACI code, which is from the center of the column, the drop panel shall extend on both sides to a distance equal to at least panel size divided by 6. Panel size divided by 6. Okay. For example, in our flat slab design example, the slab size was 25 feet and 20 feet. Okay, so along the 25 feet side, this will be 25 divided by 6 and 25 divided by 6. Okay, so this will be 25 divided by 6 on one side and 25 divided by 6 on one side. This will be the size of the drop panel. And on the others, along the other side, it will be 20 divided by 6 and 20 divided by 6. Okay. Similarly, the thickness of the drop panel, as per the ACI code requirement, shall not be less than 1/4 of the slab thickness elsewhere. So the slab thickness here is 10 inch. So this drop panel thickness should be at least 10 divided by 4, 2.5 inch. At least can be more than this. These are the two requirements for drop panel of the ACI code. Minimum requirements. For the column capital, again, there are two requirements. You know that column capital will be provided, and this will project from the center of the column in both directions, project outwards. So this angle, which is the column capital makes with the vertex, shall not be more than 45 degrees in order to control the problem of cantilever action arising in the column capital if angle is more than 45 degrees. So this angle of column capital shall be less than 45 degrees. The second requirement of the ACI code is that whenever the column capital is to be provided, then the concrete shall be poured at one and the same time in the slab and column capital, which means that column, in the case of column capital, first of all, the column shall be concrete and the column shall be poured up to the bottom of the column capital here, this location, and then the form work shall be prepared in such a manner that when concrete is poured in the slab, that concrete shall also be poured in the column capital, and column capital and slab concrete shall be poured at the same time. This will create a problem while providing farm work, because farm work for the column capital and the slab at one and the same time will become challenging at the site. In some of the situations where you see in a building that a column capital has been provided, most of these column capitals are ornamental column capitals. These are not structural column capitals. Okay, so ornamental column capital is no problem if they are provided for the aesthetic reasons. But the structural column capital shall be provided with these requirements. Integral beam and bend bars. If integral beam and bend bars are provided, there are again two requirements of the ACI code which must be fulfilled. One of the requirements is on the slab thickness. The integral beam and bend bars cannot be provided if the effective depth of the slab is less than 6 inches, which means if the overall thickness of the slab is less than around 7 inches, then the integral beam and bend bars cannot be provided. Either we have to provide bend bars or some other the drop panel or column capital or some other arrangement or some other means to control the punching shear problem. And if integral beam, the other requirement is if an integral beam or bend bars to be provided, then the 5 EC which has been calculated in the beginning shall be divided by 2 in order to calculate the integral beam reinforcement or bend bar reinforcement. This will be demonstrated in the example. Okay, in the case of integral beam, there are two things which need calculations. One is the length of these horizontal bars to be provided on top of the column in this form, and the other is the reinforcement, that is to vertical stirrups, shear strength, that is to be provided. These two is both of these shall be calculated. Okay. The length of these bars will be calculated in this manner. You know that the stirrup which are provided, the stirrups are provided on all 4 sides of this column in the slab. So the shear reinforcement will be 4 times multiplied by 2 sides of the leg multiplied by the area of bar. If you remember, in the case of beam shear reinforcement, we used to multiply the shear reinforcement by 2 because there are 2 legs of each stirrup. And here in this case, the stirrups has 2 legs, but then the stirrups are provided on all 4 sides. So 4 sides multiplied by 2 multiplied by the area of steel will give us the area of steel for 1 shear reinforcement, 1 stirrup. Shear reinforcement. Okay. This length LV will be calculated in this manner as given in the code. This blue dashed line is basically the critical parameter which has been shifted from this square type of critical shear parameter closer to the column. This has been shifted by the integral beam, and this critical parameter is now the blue dashed line. The blue dashed line parameter can be calculated in this manner. These 4 diagonals will be added, 4 diagonals, 1, 2, 3, 4, and this, which is this the vertical side, this side basically this is this column size. So if this is R, 1R, 1, 2, 3, 4R plus column size on this side and column size on this side. So if column is square, then the total parameter, which is the new critical shear parameter, after the integral beam has been provided, will be equal to 4R plus 4C. Okay, And the length LV, which is basically the length of this integral beam from the center of the column to the far end of this beam will be LV. Okay. And one of the side of this diagonal R, which is the critical shear parameter, is equal to 3 by 4 LV minus C by 2. Because this total length from the center of the column to the extreme end of this integral beam is LV, then from the face of the column to this extreme end will be LV minus C by 2, LV minus C by 2. And for the critical shear parameter, according to the ACI code, 75% of this LV minus C by 2 will form one side of this triangle whose diagonal is R, like this. So the diagonal R has a side X. This triangle whose diagonal is R has X equal to 3 by 4 LV minus C by 2 and 3. So this will be equal to, you know, that it will be under root 2 into X. The total shear parameter is B naught is equal to 4R plus 4C. For a square column, this can be calculated like this. R is equal to square root of 2 into X. Okay, and if we substitute this value of R in this equation, this will be B naught is equal to 4 into square root of 2X plus 4C. Further simplification of this will give us a value equation of B naught is equal to 4.24 LV plus 1.88 C. Okay, from this equation we can calculate LV, which is the length of this integral beam, provided we know B naught. B naught will be in this equation, the B naught value which has been calculated in the beginning will be used in the calculation of LV, which means that this B naught, which is the black dotted line, closer to the column, will give us the value of B naught, and this will be substitution in this equation, and this will give us LV. LV is the length of the integral beam. Correct? Critical parameter for an interior column. You know the size of the column is 14 inch, D is 8.5, so B naught is 19 inch. Tributary area, which means extruding area of B naught, in this manner can be calculated. So the tributary area 25 multiplied by 20 minus C plus D whole square divided by 144 is 496.5 square foot. Punching shear demand can be now calculated. We know the load is 0.3804 kip per square foot, so multiply by this. This gives us a punching shear demand of 189 kip. If we do not deduct this area, this one, so there will be only a small difference in the VU, because you know that 25 by 20 is 500 square foot. So 500 square feet multiplied by 0.3804. This will give us around 200 kip punching shear. So there is a difference of only 10 kip, and the difference in area is only 4.5 square feet. Although this difference is negligible, from the practical point of view, this for the purpose of academic requirement, we need to do calculations in this manner. Although in the design practice, we don't deduct this area of B naught plus D whole square in our calculations, because for practical reasons, this reduction is insignificant. Okay, now punching shear capacity. If we calculate this term as C prime B naught D, because this is common to all the three equations for 5EC, this comes out to be 48 kip. The first equation gives us a value of 145 kip. The second equation gives a value of 216 kip. The third one, 208 kip. The least is 145 kip. So we will compare the punching shear demand with this value of 5EC. Since 5EC 145 kip is less than 189 kip, so we need to increase the punching shear capacity of this slab in order to overcome the problem of punching shear. This can be done in many ways. First of all, let's say we want to provide drop panel. So drop panel can be provided by equating VU to 5EC. If we equate VU to 5EC and then and then substitute all the values in 5EC except D, we can calculate the minimum D which is required in order to make 5EC equal to VU. So this is 0.75 into 4 into C prime, B naught is 90 into D. So this requires a value of D equal to 11.07 inch total thickness of the slab. So either we should increase the thickness of the slab from 10 to 11 inch, 11.07 inch, so which will unnecessarily increase the weight of the slab because 1 inch concrete will be provided everywhere in the slab. Instead, if we provide a drop panel in the vicinity of the column, because the slab thickness increase in the slab thickness is required in the vicinity of the column, not everywhere. So that can be done by providing a drop panel. The drop panel requirement is now if D is 11.07 inch, the total thickness including the thickness of the slab is now D plus 1.5 inch, because this is the cover and reinforcement requirement. So 11.07, 1.5, 12.6 inch thick slab is required. 12.6 slab is required in the vicinity of the column. We know that the 10-inch slab is already been provided, so additional 2.6 inch drop panel will be provided in order to make the overall thickness equal to 12.6 inch in the vicinity of the column. There is an ACI code requirement that the thickness of the slab shall be at least 1/4 of the slab thickness. So the slab thickness is 10 inch, 10 divided by 4 is 2.5 inch. We are proposing 2.6 inch thick drop panel, so this is correct. And then the size of the drop panel. The size of the drop panel, if you remember, we said that it should extend on all sides equal to the slab thickness divided by 6. In this 25 feet sides, 25 feet divided by 6, 25 divided by 6, it is 8.5 feet. 20 divided by 6, 20 divided by 6. So 8.5 feet by 7 feet drop panel will be required, and the thickness of the drop panel shall be 2.6 inch. So this will be provided everywhere. This drop panel is for the interior column. For an edge column and corner column, you can calculate yourself. If you don't if you want to provide a column capital instead of providing drop panel, so this can be done again by equating 5:2 to VU, but this time instead of keeping D, instead of calculating D, we will calculate B naught, and then we will calculate C from B naught. 189 is equal to 0.75 into 4, this B naught. So B naught, the minimum B naught, which will make 5EC equal to VU, is 117.2 inch. And we know that B naught is equal to 4 into C plus D. D is known to us. We'll calculate C from D, which is the minimum column dimension, which will make 5EC equal to VU. Okay. And we know that this column dimension C, which is this column dimension 20.8 are when we round this up, it will become 21 inch. If it is provided all along the length of the column, this will unnecessarily increase the size of the column and putting burden on the project. So we will increase this column size at the top portion of the column. This called as column head in this manner. Okay, but keeping in view the ACI code requirements. So you will increase the top of the column from 14 to 21 inch in this manner. On both the sides, 3.5 inch column dimension will be increased, 3.5 inch on one side and 3.5 inch on the other side. Okay. Then the portion from where the column capital is to be provided will be calculated from the angle, and you know that the angle which is allowed as per ACI code is 45. The maximum angle is 45 degree. It can be less than this, but cannot be more than this. So this Y depth of the column capital can be calculated from this. If you take a tangent theta, this will be Y is equal to 3.5 divided by tangent of theta. If theta is kept equal to 30 degree, then Y is equal to 6 inch almost, which means the depth of the column capital is 6 inch. and the horizontal dimension is 3.5 inch at the top. If angle is kept 20 degrees, then y is equal to 9.62, can be provided at 10 inch. So in this manner, a column capital can be provided with the various angles. These angles will mostly depend on the availability of the farm work for the column capital at the in the market. So this will not be every time in your control. The farm work for the column capital will be already available in the market. So you should search the market and find out which type of farm work is available, and then you will adjust your dimensions according to the availability of the farm work. Okay, so in this manner, column capital can be designed. The third option is to provide an integral beam. Okay, integral beam can be provided in this manner. 5EC has been calculated, which is 145 kip. So according to the ACI code requirement, the 5EC shall be divided by 2 for the calculation of shear reinforcement in the case of integral beam. When 5EC is divided by 2, it becomes 72.5 kip. If you want to use half-inch round bar with 2-leg vertical strap having 0.4 square inch area, then there are 4 sides, so 4 into 2 into 0.4, this will become 1.6 square inch. Okay. And the spacing requirement will be calculated from this equation: 5AB FYD divided by VU minus 5EC. Phi is 0.75, AV is 1.6, FY 60, D is 8.5, VU is 189, and 5EC. 5EC, this 5EC is not 145 because as per ACI code, this shall be divided by 2, so this is 2.5. According to this, 5.25 inch spacing is required. We will round this down to 5 inch. Maximum spacing allowed as per ACI code is D by 2. With D is the effective depth of the slab, so this is 4.25 inch. We'll select 4 inch spacing and use number 4 2-leg vertical step at the 4 inch center. The last step is to provide the length of this integral beam. The length of the integral beam will be calculated from this equation: B naught is equal to 4.24 LV plus 1.88 C. We have calculated B naught in the previous slide, which was equal to 117.2 inch. We'll substitute this value in this equation. B naught for B naught, we will put this value 117.2 inch in this equation, and C, the size of the column, is known to us, so LV can be calculated. LV comes out to be 21 inch. So 21 inch from the center of the column to the far end of this integral beam. We will round this to 24 inch, and so 2 inch on one side and 2 inch on the other side, 4 inch long, 4 feet long, 4 feet long integral beam will be provided with two top and 2 bottom bars. Mostly there are no calculations done for the longitudinal bars which will become part of this integral beam, but the ACI code says that the bars to be provided in this shall not be less than number 4 bar. Okay, so this will be, mostly we use number 6 bar in the integral beam. Number 5 bar can also be used. So here we have used number 5 bars, 2 top and 2 bottom number 5 bars to hold these stirrups. And the length of the integral beam is 4 feet. The first step will be provided at S by 2. S by 2 because the spacing is 4 inch, so the first step will be provided 2 inch from the face of the column, and then the rest of the step will be provided 4 inch center to center. So in this manner, the integral beam can be provided. Okay, with this discussion in this lecture is completed. We have designed a flat slab, a flat plate for flexure, and then for punching shear with all the options: drop panel, column capital, integral beam. This is the summary of this lecture. For a particular span of frame, we will find first of all static movement, then we distribute this longitudinally and then laterally with the maximum spacing requirement. This is the punching shear element equations. So this is the end of the lecture. If you have any question, you can ask questions. Otherwise, the lecture is over now. If you want to ask questions, you can ask your questions. Okay, we will give you one example. Okay. Samula will now take over and he will discuss with you one of the examples. You can practice this, and then if you have any questions, I am here. You can ask your questions.
अच्छा, ये एग्जांपल नंबर 3 है, बिल्कुल एग्जांपल नंबर 2 की तरह है, लेकिन डिफरेंस सिर्फ इसमें ये कि इसमें डायमेंशन वो मुख्तलिफ है वो एग्जांपल नंबर 2 से। तो आप इस एग्जांपल को सॉल्व करें। ये स्लाइड नंबर इस स्लाइड पे ये प्रॉब्लम स्टेटमेंट है और फिर नेक्स्ट स्लाइड में भी कुछ डेटा वो गिवन है। तो इस स्लाइड को स्टेटमेंट को अपने साथ नोट करें, फिर मैं दूसरी स्लाइड आपको दिखाऊंगा। अच्छा, और ये बात नोट कर ले, इस प्रॉब्लम का जो रिजल्ट है वो बेंडिंग मोमेंट और फाइनल जो डिज़ाइन है वो नेक्स्ट स्लाइड में वो गिवन है। तो आप इस एग्जांपल को सॉल्व करें, फिर मैं बाद में आप को वो स्लाइड दिखाऊंगा, फिर अपना जो कैलकुलेशन हो वो इसके साथ कंपेयर करें। अच्छा, ये नोट कर ले अपने साथ, स्लैब थिकनेस वो ऑलरेडी गिवन है, वो 8 इंच स्लैब की थिकनेस है और फैक्टर लोड भी गिवन है और कॉलम स्ट्रिप विड्थ वो भी गिवन है।